Welcome to the 24th lecture in mathematical finance. So today we continue our discussion on risk measures. And in particular, we want to study now some concrete example of risk measures, which was the value at risk, and then we discuss related risk measures. So what we want to understand is well, we have a financial position. So this was, in our context, a random variable which is assumed to be at least integrable. And this is to make our life technically simpler. So this represents a financial position, and this might be a linear combination of assets, so trading in the market and European and American options. So this could be everything. So all our exposures we have in the financial market. And well, the purpose or the goal for we are currently heading to is to understand, okay, how can we assign such a financial position, so this random variable x, a way to quantify the risk we face from having this exposure in the market. So for this purpose, we introduced the idea of a monetary risk measure, and we also introduced already one example, which is still frequently used in the financial sector, and this is the so-called value at risk. Value at risk at level lambda is between 0 and 1, is given by the following formula. So var, so value at risk, level lambda of the financial position x, just given by minus the quantile. And since we have here possible non-continuous distribution, we need to decide whether we take the left or the right inverse of our distribution function. And then we normalize it with a minus because we want to quantify the risk in the sense that this is something negative. But of course, this is somehow the perspective we decided to take here. All right. What I haven't discussed last time, because I was running out of time, was, okay, what is this risk measure telling us? Okay. So this is the value at risk, and this is so. Okay, of course, in a minute I need to verify for you that this is indeed a monetary risk measure and has some properties which are rather nice. First, let's discuss the definition. So in the financial context, the var x is the minimal capital one needs to add to financial position x to ensure, right? The probability of having losses is less than lambda, right? So losses means that our financial position X or a random variable takes a negative value. Right, so this is if we have our exposure in the market modeled by X, the value at risk gives us the minimal capital, so the cash position we need to add to this financial position in order to ensure that the probability that we make losses is less than lambda. This, I mean, we talk about monetary risk measures here, so we can quantify it in cash positions. And obviously, there's a immediate criticism you might also have noticed directly. And this is that the value at risk, I mean, controls somehow the probability that we have losses, but there's no control whatsoever about how heavy these losses are. This is, I mean, a certainly strong drawback of the value at risk. Controls. And so, I mean, we can minimize with the value at risk the probability that an extreme event happens and that we have huge losses, but we cannot control anything. I cannot say anything about, okay, how bad are the losses if we are in this set with probability less than lambda. Of having losses, but not the amount. Right. Okay, this is okay. Of course, every risk measure usually comes with advantages and disadvantages. Why this is, I think, a fairly natural approach to it. It has some drawbacks, and the one drawback I just stated here. All right. But of course, the first step, I mean, after introducing now a definition of a risk measure, I need to convince you that this risk measure is indeed a risk measure, right? So I just gave you a definition how I want to quantify risk, and before in the last lecture we discussed, okay, what natural properties do we want to have to call something a risk measure? So that's the content of the next proposition, is to really convince you that the value at risk is indeed a monetary risk measure. So value at risk at level lambda is a monetary risk measure. Which had the following properties. So it is distribution invariant. So the actual realization of the financial position X doesn't matter. It's only counts how how it's distributed, and it's positive homogeneous. So if I scale my financial position by a positive constant, I also scale the risk I have assigned by the value at risk by this positive constant. All right. Okay, so this is in the value at risk is indeed a risk measure. So this is the formula, I mean, you want to keep in mind for the moment, because this is what we, of course, will use now frequently. And I mean, you saw also two other representations already included in the definition of value at risk, which we will use also today, but then, I mean, you will recall them in the proofs. Okay, so let's prove this. Proof. Okay. Okay, what do we have to check if we want to show that something is monetary risk measures? Well, there were two defining properties. The first one is monotonicity. So if my random variable gets larger, then my risk gets lower, right? So if I have always bigger payoff, then the risk of losses are less. And the other one was, it was translation invariant. So if I add a cash position, this cash position, I mean, reduces my risk assigned by the value at risk by exactly the amount of cash I added. Okay, so let's do this. First thing is monotonicity, as I said. Yes, so actually, the proof is rather simple, I would claim. But I mean, we need to get our head around these going from the distribution to the inverse, because I mean, we want to work with quantiles here. Quantiles are the inverse of a distribution function. And so this is always what we need to familiarize ourselves with. And if we have done this, then it's actually rather straightforward calculations to prove it. So let's take two random variables which are ordered here. So y is bigger or equal than x. And then, well, what do we note? So if I look at the distribution function of x at the point little x, well, you all know that this is defined as the probability that x is less or equal than small x. And if y is bigger than x, the probability that y is less or equal than x gets smaller, right? Because if y is less than x, then we also know that x is less than x, but the other way around might not be true. And this is the distribution function of y. Okay. And now we swap to the inverse, right? So by swapping to the inverse, I get the quantiles. And this means the signs you swap. So right, this signs, the greater or equal sign, the less or equal. Greater or equal sign gets less than equal sign. Oh, that's y. Right. This is of course true for all lambda in 0, 1. And now I multiply both sides by -1 to get the definition of var. This was our convention that the value at risk is something negative. So I get here my minus the quantile to the level lambda of y. And well, if I multiply this equation by -1, the sign swaps again. And here we are, that's an x and not a lambda. Right. Okay. That was easy, just keeping in mind that we always need to swap the signs in the right way if we go from the distribution function to its inverse. Second property we wanted to show is the variant in the translation invariance. Right. So what do we have here? So we take an x, and this is the cache we want to we want to add. So if we consider the var of at level lambda of the random variable x plus little x, so our cache position, we want to show that this is the same as the value at risk of x and then plus little x. All right. So let us recall, I mean, this identity we have like shown last time in the definition. So this in the value at risk is given by the infimum of all real numbers m, such that the probability of the random variable x plus m is less than 0, is less or equal than lambda times 0, lambda. Yeah. I mean, this is a representation we have already seen. We can recall from last time. Okay. And now let me introduce m tilde, which is just, let me define m tilde to be m plus x. So this is just definition. And if we do so, we can add here. So we replace the m by an m tilde, and then we get a minus x here to have the same expression. Right? And now, or what is this? So m tilde. Here the x are canceling, so that's very simple. Actually, it's not worth another line. So this is x plus m tilde is less than m, less than 0. So the probability that x plus m tilde is less than 0 should be less or equal than lambda. Well, and this is nothing else than the var at level lambda of the random variable x minus x. Oh, sorry. If I have here my minus on the right, so if I add here, so if my m tilde is x plus m, I can subtract here the x as well, and here the x, and then we get what we wanted. So, I mean, this was not wrong, but you can always shift it. Okay. So that's so we know now that the value at risk is indeed a monetary risk measure. And now I promised you two more properties. The first one was the property that it's positive homogeneous. So if we scale up our financial position x by a positive constant, we scale up the risk in the same way. So where's our positive constant? Let's call it alpha. What do we get if you have alpha? So we want to consider the value at risk at level lambda of the financial position alpha times x. And now we want to pull out or verify that we can pull out the random variable, the constant alpha. All right, let's do this. Again, we use here our representation we verified last time. So this is all the probability that alpha times x plus m should be less or equal than lambda, and we want to show the infimum of M fulfilling this property. Well, that's not right. Same as we used for the translation invariance. Okay, and now we introduce a new M star, M tilde, and M tilde is just now M divided by alpha. Right, new definition. Same trick as before, but with a different choice of tilde, M tilde. And this gives me here an alpha, and now I multiply it with M tilde. So nothing happened here. It's just a relabeling of deducing the auxiliary constant. But you see here why I want to have that alpha is strictly positive in order to be able to do this. Okay, so this is equal to the infimum of alpha times M tilde, and now, well, this is negative if and only if M plus, so I can divide both sides by alpha to get that this is the same set. And well, here we are, that's nothing else than alpha times the value at risk and the level lambda of the random variable X. This is exactly what we wanted to show. Okay, and I promised you a last property, which was the distribution invariance. So let me provide you with the last property as well. Okay, what do we have here? Okay, here actually it's nothing to do. So I write something which you should not write in an exam. And I claim that this is obvious. Okay, indeed, I mean, in this time it's really obvious. Because let's scroll up to see the definition of the value at risk. Well, the very definition of the value at risk doesn't depend on the realization of X. It's defined by its distribution function. So every random variable which has the same distribution function creates the same value at risk. So there's, I mean, it does not depend. It only depends on the distribution of X. Okay, that was nice. Or at least simple for me. All right, now one warning. The value at risk is not convex and such not coherent, right? I mean, for coherent, it's, I mean, we have the positive homogeneity, but we are not convex in general, so it cannot be coherent. Risk measure. So what does it mean here? So there are situations that the value at risk might penalize that we take a diversification of financial position. And actually, I mean, we discussed this, and this seems to be this seems to be a very natural property that if you spread your financial position over several assets, this should somehow reduce the risk of heavy losses. And the value at risk, I mean, I mean, there's a situation where this is not the case. I mean, this is the value, the value at risk might assign you a bigger risk if you start splitting your capital, which is unnatural. And here, I mean, it's not so bad because in most example situation, this is not the case. And then the main problem on a mathematical level why this might happen is that if your distribution function has some discontinuities, and if you run into them, they might destroy the convexity property. And that's on a hand-waving meter level. I mean, you can sit down and construct you a distribution where exactly this happens. But okay, this is not, I mean, this is not the main criticism about the value at risk. The main criticism I would claim is that you have no control about how heavy your losses are. But it makes sense to, I mean, to get this desired property of a coherent or convex risk measure. And in order to do so, I mean, we want to modify the definition, or researchers have modified the definition in order to ensure this property as well. And this brings us to our next example of risk measures. So this is (7.2) is the average value at risk. Right. So the aim is to get a convex or coherent risk measure, and there's several ways to ensure this based on the, or closely related to the value at risk. So let me give you directly the definition, and then we study what this means or why this has the properties we want to have. Okay, what do we do? Okay, we want to keep our level. So lambda is a number between 0 and 1. And we want that Q denotes be our lambda quantile, which, as you might, I mean, this is the set, but here it actually doesn't matter which one you pick. So pick lambda quantile of our financial position X. All right. And now I want to give you 3 definitions of hopefully coherent risk measures. The first one is the average value at risk. At level lambda of X, and X is, okay, a random variable in L1. So now, I mean, oh, that was bad. Here we go again. So I told you that the issue with the value at risk of not being convex is basically created by the discontinuities of the distribution function, the quantile function. And this is of course related to the discontinuity of the distribution function. So there's a simple trick to make our life smooth. I mean, you might have seen it in different settings in or different courses in your studies already. So the trick is you just average. So this is, I mean, integrating something has a smoothness property. And since, I mean, we have here countable many discontinuities, if we average over an interval in R. This is the null set. This means we have something which is almost surely not discontinuous. So what we do here, if we have a given level lambda, so we average over all levels which are worse up to the level we want to have, and then we normalize it to have an average. And then we integrate the value at risk at level gamma from 0 to lambda of the random position. Right. So instead of considering one specific level, we say, okay, we consider all levels which are worse up to lambda, and we integrate over it. Because I mean, you don't want to have bad luck and be in a singularity. So we smooth it over. A trick which always works. Okay, always is a meter statement and not a mathematical theory. Okay, this is one way. Next idea is to work with the expected shortfall. And level lambda of x. And this one is given by the following definition. Let me again. So expected shortfall here is expected shortfall of level lambda of x is, okay, this, by the way, definition, again, the definition here is minus lambda, I1 over lambda multiplied with the expected value that x, so the expected value of our financial position conditioned on x is less than the quantile at the level lambda. And now we want to penalize this for the discontinuities here, right? And we here put here a term which disappears if we have a continuous distribution function. Right, so basically we take the average, so the expected shortfall, we take the average over the values of our financial position in case we have x takes some loss. So let me give you directly the remark in order. I mean, so let here's some space. I will use this in a minute. So this is the remark 7.9. So what we have here. So if you assume, but we are not assuming in general, we're just assuming this for the remark here. So if the distribution function f of x, so the distribution function of our level here is continuous, right? So probably this is the natural situation in any application, right? So yeah, I think this is, because every discontinuous function you can always, as I said, smooth a bit, and then you have continuous function. Anyway, so if this is continuous, what do we get? Well, then the probability of x being strictly then q is exactly lambda, because this is the quantile at level lambda. So this basically means yeah, the quantile is uniquely defined. And this means that the expected shortfall at level lambda of x is nothing else than 1 minus lambda. And then the expected value that x of x conditioned on the event x being less than q. And now I have minus, right? I give you my minus, and what is this? Well, this is nothing else than x given the sigma algebra generated here by x being less than q. Right. So you see, I mean, this is expected shortfall. So this is the expected value, or minus the expected value. So the expected losses we have if we condition everything on the scenario that x is less than the quantile q. All right. And now there's another way, which is the called conditional value at risk at level lambda of x is, so this is the conditional var level lambda x. So this is defined as, well, lambda over lambda, so a normalization constant, and then the expected value of the negative part, so that the x is less than q, right? This is only a positive number if x is less than q, and then I make sure that it's negative by subtracting q. Okay. Oh, and here we are. Right. Okay. So before, I mean, I keep discussing these three objects, I want to show you that these three objects are actually all the same. Okay. Lemma 7.10. For lambda in 0, 1, what do we have? Well, the average value at risk of level lambda given x is the same as the expected shortfall of level lambda of x is the same as the conditional var of x. Right? So, I mean, mathematically speaking, they're all naturally to introduce, and you can think about it and what they mathematically tell you. So they appeared in different contexts as natural risk measures, and they all lead to the same object. As indicated already by my title of this section, right? This is all the average value at risk. But you have here a nice interpretation by expected shortfall or conditional value at risk. Okay, so we need to show this. Let's do this. And well, first we show that this definition all gives you all one type, I mean, one risk measure, and then we will show that this is, I mean, as I promised you, is indeed a convex or coherent risk measure. All right, proof. Okay. So let me start with some preliminary observation. So for, okay, lambda is always between 0 and 1. What do we notice? So if I look at the expected shortfall, x, and let me rewrite this is just recall for you the definition because we just have seen them. So to familiarize yourself with this definition, let's write it down again. This is minus lambda, so 1 over minus lambda multiplied with the expectation of x, that x is less than q, and q is here our quantile as before, our number, plus q times minus lambda minus the probability that, right, to take care of the singularities, the discontinuities of the distribution, right? And now this is equal to let me give you, so what we observe as well is that x, so the expected value of x being equal to q, right? So x times the indicator function that x is equal to q. Well, we can calculate this explicitly. This is nothing else than q, right? On this set, it's, the random variable is either 0 or q. And if it's 0, well, it doesn't matter. And if it's q, then this happens with the probability p of p that x equal to q. Okay, that's not very deep. But this means we can add here so we can add that here, this is the new thing. Less or equal instead of a strictly less. And then we have to subtract this as well. So minus x less or equal to q. Right. All right. And I want to give this number because I did this pre-observation because I want to use it. Okay. So what you keep in mind if I refer to 7.1 is, okay, you can define the expected shortfall also with less or equals than rather than strictly less. Anyway, step 1 is the first quality you want to show. To show, what do we want to show? Okay, we want to show first that the value at risk, as the average value at risk, level lambda of x is equal to the expected shortfall. Right. Okay. So how do we do this? First thing I would like to note is we can always extend our probability space to find a random variable u on, let's assume it's the same probability space. Random variable u, which U is uniformly distributed, on 0, 1, right? This means the probability of U being less than little u is exactly U for all U in, this is just what uniformly distributed means. And I mean, why do I write without loss of generality? I mean, we might need to extend the probability space so that this object really exists, but I mean, you're all very familiar with probability theory, so that's not an issue here. And we know that if we define the random variable z given by the inverse function of the generalized inverse function of the distribution function of x, and then we put u inside of it, and then this has the same distribution as x. All right, you might have seen this already, otherwise just verify that the distribution function are the same as a 2 lines calculation. All right. So this is more an auxiliary object in order to understand the calculation. So we want to show this here, right? That's our goal. All right. And for this, well, again, we need to get our head around these inverse functions. So first thing I see here is, I look at the inverse function of x. Well, this is non-decreasing because it comes from a distribution function, which is non-decreasing. Okay, that's nice. And what do we see again else? I mean, if we look at the event that u is less than lambda, this is included in the event that z is less or equal than taking the inverse. The distribution from x in order to lambda. Right, I mean, this means just we take this equality and we apply the inverse or the generalized inverse of the distribution function of x to both sides. This gives us the definition of z, and this gives us this. And since this might be not a continuous object, we might add some elements in there. I mean, as I said, I mean, our life would be much easier if we just assume just that the distribution function is continuous, but we don't. To keep the level of fun up. All right, second observation is, okay, I mean, if you want to understand what is in there but not in there, so we want to consider the event that u is strictly bigger than lambda, but z is still less or equal f, the inverse x of the distribution of x applied to lambda. Right, so this includes elements which are not in here, but in the second set. And what we see here, well, by the definition, this means here we always have, I mean, this is included in z is equal to lambda. Right? So the omegas which are not in here but in here, they fulfill this. I mean, we need to have here the equality. Okay, that's nice to observe because we can use this in our calculations. Okay, now we want to calculate the value at risk. And in order to calculate the value at risk, what do we need to calculate? Well, we need to calculate the integral from 0 to lambda of the inverse function of x given a level gamma. Right. And this is what we want to calculate, and we want to relate it to the expected shortfall. Okay. So what is this? Okay, that's nothing else than z, right? This is function z. So this is the expected value of z because this is z, and then integrated in probabilistic terms over u being less than lambda. Right? So I mean, this is an integral. I mean, lambda is between 0 and 1. So we use now our auxiliary random variable to just rewrite it. And the expected value of z, right? And this is, I mean, if you plug in here u, this is what you have. So, right here you have the definition, and you integrate only up to lambda. So you multiply with the indicator function of u being less or equal than lambda. Okay. That's nice. Okay, what is this? Well, this is nothing else than I apply here my inverse distribution function. So if I apply this, my u becomes a z, and here I have the inverse of the distribution of x applied to lambda. Right? And now it's even better. I mean, if I have done this, I mean, I enlarge the set as we discussed here. So we need to subtract this here because this is the things we added, which we didn't want to add to have the equality. Okay, so this is u bigger than lambda intersected with z being less or equal 1 to the power minus the inverse of x given lambda. Okay. Yeah. All right. Let's keep the equality here. Okay. Okay. The first thing is, okay, let me move this up here a bit. So that's easy. So let's keep this one because this looks good. Right, but if I'm on this event, I know my z is equal to f inverse of x lambda, and then the expected value of this indicator function. Because on this indicator function, we know, I mean, how to calculate. I mean, we know that z is equal to this value. Right. So this is just the indicator function. Okay. Okay, as I said, the first thing already looks good, so we have to keep it. Want to keep it. Yes. Okay, now we need to understand a bit better. That's lambda, and this is lambda. So what is this? Well, this is nothing else than 1 minus the indicator function of u being less or equal than lambda, right? Yeah. Times, or we have here the second indicator function, that being less or equal to the inverse of x given lambda. Right. Okay. Again, copy pasting the first part. Okay. So let's calculate this again. So what is this? Well, let's make a bracket for the linearity here. So we have first 1 times the second indicator function. So we get the expected value of the second indicator function. Minus, well, the other 2 indicator function, u intersected with z. Oh, that's not an x, that's lambda. Wait, and now I need to get here somehow a bracket. Yes. Cool. Last line. Now we're almost done. We see we slowly converge to what we want to have, namely the expected shortfall. So we keep the first term because we're already happy with it. And now we calculate here the expected value. So I mean, this is the negative, so we move it. We multiply it the -1 or pull the -1 out, and then we calculate this one first. So this is nothing else than lambda. Right, this is here lambda. I should wait. And we also have the second one. Well, this is nothing else than the probability of x being less or equal than bracket. All right. Okay. That I mean, it looks like a long calculation, but they're really tiny reformulation line to line, just to familiarize ourselves with the inverse quantile functions. So now we divide both sides by sides by minus lambda. What do we get? Well, if we both sides, let me show the side here. So if you divide the right hand side, oh sorry, it's left hand side by minus lambda. Well, this is just the definition of value at risk, average value at risk. Okay, that's good. Right, lambda. Gamma x. And so that's right. Okay, and this is the right hand side, as I promised, just the average value at risk. And now we have to divide the other side by minus 1 over lambda as well. So what do we get here? So that's the right hand side. I mean, here nothing happens. I'm just copy pasting the right hand side. Okay. All right. Okay, what is this? Well, this is nothing else than 1 minus 1 over lambda. What is this? This is the expected value of x. Well, I mean, this is just equal to q, so x q is the quantile of at level lambda. Right, so we have here this nothing else than this here. And so we just replace now the inverse function by q. Here's q times lambda minus x being less or equal than q. And this is nothing else by then the expected shortfall, keeping in mind 7.2, right? This is, if you go up again, right? So 7.1, sorry, right? The expected shortfall, I mean, we can put here the less or equal sign instead of the strictly less sign, right? And this is good because this is what we have here. And this is then a 1. Okay. So that's the first step. The average value at risk is equal to the expected shortfall. The second step is easier, so don't worry. I mean, the calculation gets here easier. Step 2. So what's missing? We want to show that the expected shortfall at level lambda x is equal to the conditional var level lambda of x. Of course, for all lambda, as usual, between 1 and 0. Right. All right. So let's calculate. I mean, this is now, as I promised, this is not a very long calculation. So what is the conditional var at lambda of x? Well, this was by definition 1 over lambda multiplied with the expected value of the negative part. So the expectation of the negative part here of x minus q minus q. Okay. So that's nothing else than 1 over lambda. And the expected value of x minus q multiplied with the indicator function that q is less or equal than, that x is less or equal than q minus q. Right. Now let me, so this is 1 over lambda. Well, so we can calculate the expected value a bit further. So this is q times q times the, I need to swap you the sign, sorry. Right. You want to ensure that it's always a positive thing. So that's q times the probability that x is less or equal than q minus the expected value of x multiplied with the indicator function that x is less or equal than q. And if we now pull out here the indicator function, add the 1 over lambda, right? So we added here bracket. It's horrible bracket. Sorry. We write it again. Then we have here lambda times q. Okay, that's not super hard. Okay, cool. So what is this? This is okay. We want here a minus to get the definition of expected shortfall. So minus 1 over lambda. And if we put here minus, well, we need to swap the signs. So this is this goes here. So we have the expected value of x times the indicator function of x being less or equal than q. Okay. Plus, and now well, we have here q and there, q here, q and here, q. So we pull out the q, and then we have lambda minus probability of x being less or equal than q. It's nice. And this is just the expected shortfall, lambda x. If we again keep in mind the our identity, right? The preliminary calculation that we can equivalently define the expected shortfall by making here less or equal instead of strictly less. Okay, cool. So we're done with the proof, and well, the message here is all these three definitions, so the value, the average value at risk, the expected shortfall, and the conditional value at risk lead all to the same object with the different mathematical interpretations. And so they are them. But now, I mean, I need to, of course, convince you that the objects I just introduced are indeed coherent risk measures, monetary risk measures. And what's the better way to convince you than proving it? Okay, so for lambda between 0 and 1, the average value at risk, and so in particular the also the expected shortfall and conditional var at level lambda is a coherent risk measure. Okay, let's change the color. Proof. Okay, let me, so the note. Oh. Okay. Okay, what do we know? First thing, monotonicity. Translation invariance. Invariance. And positivity, positive homogeneity. Follows from the same properties as of the value at risk. Right. So monotonicity, translation invariance, and positive homogeneity have we already shown for the value at risk. And now if you go back to the definition of average value at risk, right. Here we are. Right. If you can pull out, I mean, if it's monotone, if the integrand is monotone, the integral is monotone as well. So that's easy. The translation invariant, well, since you have here an average normalized by 1, so if you can pull out the cache position here, you can also pull it out at the integral. And last thing, you Um, Nothing. What? Yeah, invariance, right? Wait. So now I moved. Was so should I still show translation invariance? Positive? Yeah. Okay. Right. Okay. So this, I mean, we have verified this property for value at risk. So we immediately get them for the average value at risk as well. The only, I mean, thing which we really have to show now is that it's a convex risk measure. And this is new. I mean, this was not true for the value at risk. And now I was claiming by averaging the value at risk, we get a convex function as well. So since it's positive homogeneous, so we need to show the convexity. It is sufficient to show that, well, we are already positive homogeneous, as we know, so it's enough to show that it's subadditive, the average value at risk, right? So if I have to consider the average value at risk of a sum of two random variables, I can estimate it from above by the average value at risk of x plus the average value at risk y. These are, of course, random variables in L1, right? Because I mean, if you plug in here alpha and here in front of the y 1 minus alpha, and alpha is between 1 and 0, there's a positive constant, so you can pull them out and you see the definition of convexity. All right. So that's what we wanted to show. Yes. All right. No. All right. I mean, as in the proof we have seen before, to verify such a property, it's helpful to find, I mean, to choose the best representation, I mean, the most suitable representation to get this property. So, okay. Our last lemma what do we know? We know that the average value at risk at little lambda of x is equal to the expected shortfall, right? And this is and this is just the definition here of the expected shortfall. Right. Bracket missing. I hope no, I have all brackets right. And what is this? Well, this is nothing else than 1 minus lambda. Okay, let's keep the first one. And now I put in here a delta, which I define in a minute, or in the next line. I put here delta of x. Then the multiplied with the expected value of x being equal to x multiplied with the indicator function of x being equal to q. Okay, it's pretty obvious what the Q lambda, the delta lambda of x has to be. Well, it's 0 if the probability of x being equal to q is equal to 0. Right, then this term is 0 anyway. And otherwise, this is just lambda minus x, the probability of x being strictly less than q divided by x, the probability of x being equal to q, if otherwise. Okay, let me briefly check this again for you. I mean, this is not hard, right? Because I mean, if this is true, this term is 0, and if this is true, they cancel to get the same expression. So wait, let's check this. Let's give this a first number because we want to use this representation. So that's 7.2, and let's check 7.2. Check 7.2. Right, since Q is a lambda quantile for X, what do we mean by this? This is just the definition of a lambda quantile. So the probability of X being less or equal than Q has to be bigger or equal than lambda, and the probability of X being less than Q has to be less or equal than lambda. Okay. Well, this implies, so this is by definition. So my delta of lambda of X is between 0 and 1, right? Okay, it's this is okay 1. And if we have that the probability of X being equal to Q is equal to 0, then we actually have that the probability of X being less or equal than Q is, I mean, strictly bigger than lambda, right? This is the definition of a Q quantile. And this is then equal to the probability of Q being less than and the probability of X being less than Q, and this is then, well, again, by the definition of a quantile, is equal to lambda, right? This is what I meant. I mean, if there is no mass at the quantile Q, then the quantile Q is uniquely determined. In other words, lambda minus X minus the probability of X being less than Q is exactly equal to 0. So this means in the first case, so if we are in this case here, then the proof is done, and otherwise we just plug in the definition. If X, so if we have mass and X being equal to Q, then, well, here 7.2 follows by plugging in the definition. Right. All right, so we have this nice representation 7.2, and we want to use this to show that the average value at risk, or here the expected shortfall at lambda, is subadditive. Okay, let's do this. From 7.2, we know the average value at risk at level lambda of x is nothing else than the expected value of minus x and then an indicator function, which is not strictly speaking an indicator function. So this x being less than 2. Okay, I need to define for you what I mean by this. This is just a short writing I want to introduce to save some time. So this is defined as 1 over lambda multiplied with the indicator function of x being less than q plus this function delta times lambda x multiplied with the indicator function x being q. Right. So if we go up here, I mean, this is just, so we put this here, and so we just label it. So we just put all the terms which are not minus x into this definition of this new one function, one indexed by lambda. So there's nothing really going on. And now we might recall, okay, as usual, these are my quantile functions. So qx, qy, and to qx plus y be the lambda quantiles of x, y, and x plus y. All right. So note the following identities. They are true for x, y, and x plus y, right? Because they're all quantile functions. You can check them in a rather straightforward way. So if I consider here my function 1 lambda, the expected value is always 1. If I look at this lambda function with the condition to the set that O, right, minus so I mean these identities here, they follow right away or from the definition. So if this is bigger than 0, if x is bigger, strictly bigger than the quantile of x, and this is strictly less or equal than 0 if we for okay. And this follows directly by the definition. But this is what we want to use now to see the to the sub-additivity. So what we want to, in order to check the sub-additivity, we the average value at risk of level lambda plus we need that, well, this difference here is greater or equal than 0, right? This is what the sub-additivity is. So then we want to check that this here is, and for this we want to use our representation, of course, we just introduced. So this is nothing else than, so that's 7. What number was it? Did I give it a number? No, I didn't give it a number. So this is the expression we have here. We had the identity we expressed, the deduced from 7.2. Right, the same here with y. And oh, that's a plus, of course. And now minus, and now we have here the same for x plus y. And of course, the indicator function here defined. Right. All right, that's good. Now we are almost done. I mean, we just want to use our identities we derived here. Oh, I need to. Right, so that's nothing else than x times. So we sort everything to have an x. Then we have x plus, so that's right, because minus here x gives me this, and then I have here minus I1 lambda x, right? Okay, that's good. And then we have the same for y. So we have here y. So x plus y. Right. This is all right. And now I use the estimates. I mean, we have seen here, so actually here we use this too. So we have here q times to the quanta of x time. We can estimate this from below. Okay, I'm running out of space here, so let me. Right, so you estimate it from below and you start calculating, so you get -1 and include this. So, and now we have here for the second one this q, and again 1 minus 1, right? Because they all integrate to 1. And that's good because this is 0, and this is exactly what we wanted to show. I mean, this looks a bit nasty, but this is really just plugging in the identities we just derived and using them to see that this is actually equal to 0. All right, let me stop here with the risk measure. So what we have learned is if we take the average valued risk, we have indeed a coherent monetary risk measure, which is actually also distribution invariant. So it's a rather natural object to quantify the risk of a financial position. All right. Next time we will briefly in one lecture discuss the transition from a discrete time world to a continuous time world, which is also like a bit of an outlook for the courses Advanced Mathematical Finance and also to some amount to the Wahrscheinlichkeitstheorie 1. So the last lecture, so this lecture is still part of the exam. The next one is part of the course, but will be not part of the exam anymore. So if you feel like, so I hope you all watch also the last lecture next week, but I mean, the last lecture is additional material, which I hope you all enjoy, but it will be not part of the exam anymore. But this course, I mean, up to now, everything will be examined. All right. Well, thank you very much for watching.